Welcome to AI Paper Slop. Today we're doing a deep dive into the source material of a really fascinating summer 2026 paper by Petra Schwer.
Yeah, she's a professor of mathematics at Heidelberg University.
Right. And the paper is titled How to Read Mathematics, a Study Guide. And to give you all the immediate summary right up front, the core insight here is that engaging with dense mathematical texts, like, the ML architectures you read every day, requires completely abandoning the pages per hour metric.
Exactly. You have to trade it for hours per page.
Yeah, which sounds painful, but she outlines this rigorous 5-step active reading framework to actually make it work. So it's overview, understanding definitions, deconstructing proofs, practice, and rebuilding the big picture.
And crucially for you listening, she caps this off with a massive warning about AI, which is backed by some really wild 2025 EEG studies.
Oh, the EEG data is mind-blowing. Basically, outsourcing your mathematical struggle to LLMs doesn't just bypass your learning. It literally creates cognitive debt and physically weakens your brain's connectivity.
It's a huge claim.
It really is.
Yeah.
So let's break down the optimal way to read complex math and why your brain actually desperately needs that friction.
Yeah, because this whole concept is frankly a massive departure from the current culture in tech. I mean, the default behavior for all of us is just to optimize for speed, right?
Oh, absolutely. Skim the abstract, look at the charts, maybe check a pseudocode snippet, and you're done.
Right, and then immediately move on to the next preprint. But Schwer is arguing that applying that exact speed reading mindset to actual mathematical texts is, well, it's the fundamental reason so many engineers just hit a brick wall when they try to adapt a new architecture.
Okay, but I'm going to push back on this right out of the gate because I can hear you guys shouting in your cars right now. Hours per page.
I know, it sounds intense.
It sounds intellectually romantic, right? But I have a product shipping on Friday. If I'm trying to implement a new diffusion model or figure out some novel attention mechanism, how can anyone in this industry actually afford to spend 3 hours on page 2 of a 40-page paper?
I mean, it's a completely fair objection, but you have to look at the massive cost of fake understanding.
Fake understanding?
Yeah. If you just skim the math and use a library someone else built, you're fine until the model does something weird. And at that point, if you don't actually understand the underlying mathematical bounds of the algorithm, you literally cannot debug it.
You're just guessing at that point.
Exactly. You're just tweaking hyperparameters blindly. Schwer makes this point that time and repetition, they aren't just optional study aids. They are biological prerequisites. Mathematical ideas need time to, as she puts it, simmer over several days.
Simmer. Yeah, you can't just microwave comprehension in a single afternoon.
Right. You just can't force it through sheer willpower.
So practically speaking, what are we actually supposed to be doing during those hours? Because it can't just be staring blankly at a PDF, waiting for the math gods to bless you with inspiration.
No, definitely not. It's really about mapping the exact boundary of your ignorance.
Okay, I like that phrasing.
Yeah, so when you get stuck, your natural instinct is usually to ask a really broad question. You might think, I don't understand definition 3.1, or, how should I interpret this matrix?
Which feels like a valid question when you're frustrated.
It feels valid, but Schwer points out those questions are functionally useless. They give your brain nothing specific to solve. You have to ask precise questions.
Right.
She gives this great example. Instead of just saying you don't get it, you should ask, why must the inverse function itself be bijective in this definition?
Okay, let's actually unpack that specific example, because throwing around terms like bijective without explaining them is exactly what alienates readers in the first place.
Oh, totally.
So for anyone who hasn't taken discrete math in a minute, a bijective function just means a perfect two-way street. Every single input maps to a unique output, and no outputs are left unmatched.
Exactly. It's a strict one-to-one correspondence.
Right. And if a function isn't bijective, you can't reliably reverse it. You might have two outputs mapping back to the exact same input, which just breaks the whole logic.
Right. So when you stop and ask, why must it be bijective, you are actively testing the structural integrity of the math. You aren't just generally confused anymore. You are interrogating a very specific constraint.
Which naturally brings us to the next foundational rule she sets up before we even touch the 5 steps. And that rule is, reading is writing.
Yes. This is non-negotiable for her.
You cannot just run a digital yellow highlighter over a theorem and call it a day.
Because highlighting is basically just outsourcing your memory to the paper.
Yeah, it creates this total illusion of competence, it's yellow now, therefore it is in my brain.
Exactly. But Schwer is adamant that you have to write summaries in your own words. If the author gives an example, but, they skip a few algebraic steps to save space, which they always do.
Always. The proof is left as an exercise for the reader.
Right, the worst sentence in academia. But she says you have to write out every single one of those missing steps yourself.
Which brings up this incredibly relatable tension she points out. It's this mental battle between keep going and move forward.
Oh, yeah, the grind.
Yeah, so you're grinding through a really tough line of a proof, and you have to decide, do I sit here and stare at this single equation until it finally clicks, or do I skip ahead and see if the next paragraph actually explains it?
It's a tough call.
It reminds me so much of bebeing stuck in an infinite while loop while you're debugging code. You could just keep running the same trace over and over, and you're getting nowhere. How do you know when it's time to break that mental loop and just read ahead for broader context?
Well, the break condition for that loop relies entirely on those precise questions we just talked about.
Okay, how so?
So keep going means you don't just give up the second a symbol looks weird. You put in the initial effort to parse the variables, isolate the exact confusion, and write it down.
Right, you do the work first.
Yeah, but if you have formulated your precise question and you've written out the steps and you're still completely blocked, that's when you have to move forward. Break the loop.
Just jump ahead.
Exactly.
Right.
Because very often, the author is going to use that abstract mathematical object in a practical context just a few lines down. And seeing it actually in motion will make that original dense definition click retroactively.
That makes total sense. So that's the foundational mindset. We're abandoning speed, we're writing everything out, and we're balancing the grind with the need for context.
Right.
So how does Schwer recommend we actually start reading the paper? Which takes us to step 1, getting a quick overview. And this step is surprisingly casual.
It is intentionally casual. She actually notes that her son does this step while reading on a swing in the yard.
On a swing, I love that.
Yeah, you don't need a desk for this part. The goal is purely structural. You're literally just skimming to ask, what is this text about? Where are the logical sections? Where are the really dense clusters of new equations?
You're just mapping the territory.
That's all it is. You're priming your brain for the topography of the paper, noting what feels familiar and what looks absolutely terrifying.
Right, finding the dragons on the map.
Exactly. But once that map is drawn, step 2 requires a completely different environment. She explicitly states you need a quiet, focused space to understand definitions and statements.
Because definitions are the literal source code of the mathematics. If you don't get them, the rest of the paper just won't compile in your head.
They are the absolute vocabulary. So when you hit a definition, you have to interrogate it. You have to ask, is this just a minor technical tool they introduced to make one specific proof work later on, or is this the central architectural concept of the entire paper?
Right, like why is it defined in this highly specific way?
Exactly.
And this is where she drops what I think is the most actionable piece of advice for our audience. She states that there can be no definition without examples. But far more importantly, you absolutely must find non-examples.
Yes, the non-examples are critical.
You have to physically find an object that looks incredibly similar to the definition, but fails just one single condition.
Because finding the non-example is the ultimate test of your comprehension. It defines the negative space around the concept.
It is exactly the same mechanism as adversarial training in machine learning.
Oh, that's a great comparison.
Yeah, like if you want a neural network to truly understand the boundary of a classification, let's say identifying a stop sign, you can't just feed it 10,000 perfect, sunny, beautiful photos of stop signs.
Right, because it'll just memorize the color red.
Exactly. It'll just learn red octagon. You have to feed it adversarial examples, like a red octagonal sticker on a laptop, or a yield sign, or a red speed limit sign.
You have to force it to fail.
Yeah, you have to actively search for the edge cases that fool the network to define where the boundary actually lies. So to truly internalize a mathematical definition, you have to adversarially train your own brain with edge cases.
That is a phenomenal way to visualize it, yeah. The non-example forces you to understand why the author drew the boundary exactly there in the first place.
Right.
And Schwer applies that same adversarial logic to lemmas, theorems, and corollaries, too. She actually suggests treating them like short stories.
I love that framing. Like, the mathematical objects are the characters, and the theorem is the plot of how they interact with each other.
Exactly. And you interrogate those stories by asking, what happens if the plot changes?
Right, like an alternate ending.
Yeah. If we drop one specific assumption from this theorem, does the whole mathematical statement break? And if so, why? If you understand exactly how a theorem collapses when a condition is removed, then you truly understand the theorem.
That's brilliant.
She also warns, by the way, never to skip the remarks or the notation sections. They aren't filler. They establish the physical laws of the universe that those characters operate in.
But, okay, mapping the vocabulary in a quiet room only gets you so far, right? Just knowing what a tensor is doesn't mean you understand how it transforms data in a completely novel architecture.
Right, knowing the words isn't reading the book.
So how does Schwer recommend we actually watch these objects interact? Which brings us to step 3, deconstructing the proofs.
Yeah, and this is usually where the bulk of your time is going to be spent. Schwer advises treating every single proof like its own mini-text.
Okay, so breaking it down further.
Yeah, you run a microversion of step 1 on it first. You just skim the proof to identify the overarching architecture of the argument. Like, is this a proof by induction? Is it a proof by contradiction?
Right, figure out the blueprint before you start hammering the nails.
Precisely. And then you go back and read it line by line. You have to track exactly where every single assumption you read in the theorem is actively deployed in the proof.
Because proofs aren't just there to, like, legally verify that a statement is true.
No, not at all. They are blueprints showing you the hidden causal wiring between these abstract objects.
So once you've tracked all those causal connections, you move to step 4, which is working through practice problems.
Yeah.
And for a research paper, this usually means trying to implement the math in code, or maybe deriving a specific edge case yourself. And she stresses that you should look at the problem sets immediately, like don't wait until the end.
Right, you get them in your head early so your subconscious can kind of chew on them while you're reading the rest of the text.
But here is the critical pivot of her entire framework. Just having that aha moment in your head, it is entirely insufficient. You have to actually write the solution down formally and clearly.
You could put it on paper.
We really need a better analogy for this because I think people constantly underestimate how brutally hard it is to write out math that you think you already understand.
It's so humbling.
It's not like recognizing a song on the radio versus playing it on a piano. It is exactly like compiling code.
Oh, I like that.
Yeah, like reading the mathematical proof is just looking at the source code in your IDE. It looks clean. The syntax highlighting makes perfect sense. You're nodding along like, yeah, I get this.
Right, it feels completely intuitive.
But writing it out yourself from scratch, that is physically hitting the compile button. And the compiler is completely ruthless.
It catches everything.
It catches every single syntax error, every uninitialized variable, and every massive logical gap that your eyes just conveniently skipped over when you were skimming.
I completely agree with that analogy. When you translate that abstract logic floating around in your head into formal, rigorous notation, you are acting as your own compiler.
Yeah.
And there is a profound biological reason why this specific friction is required. You aren't just filing away a new fact in your brain. You are physically altering your brain's structure.
Right, literally, physically altering it.
Literally. When you struggle to connect concept A to concept B, your brain responds by wrapping myelin around those specific neural pathways.
Okay, myelination.
Yeah, that myelination process is what makes the neural pathway faster and permanent. If you only read the proof, you're just taking a guided tour of someone else's neural pathways.
Wow.
But when you hit compile and write it yourself, that friction forces your brain to build its own machinery.
Building the biological machinery. Man, that perfectly sets up the final phase, step 5, and the massive red flag this paper delivers about the current state of our industry.
Oh yeah, this is where it gets really real.
So step 5 is where you finally pull back out. You've been deep in the weeds, grinding through line-by-line proof deconstructions, acting as your own compiler. Now you have to rebuild the big picture.
Right, you zoom back out.
You go back to your structural overview from step 1, you take structured notes, and you integrate all those hard-won, tiny details into a holistic understanding of the paper. You basically make sure you haven't lost the forest for the trees.
And let's be fiercely honest about the reality of working in 2026 here. When you are exhausted from step 4, there is this massive, almost gravitational temptation.
Oh, I know exactly what you're going to say.
You just want to drop the PDF into a chat window and type, "Summarize the big picture for me."
It's so easy.
Or even worse, you use the LLM during step 3 to explain the proofs to you so you don't actually have to track the assumptions yourself.
And this is exactly where Schwer issues this incredibly strong caution, which is backed by some very sobering empirical data. Because mathematics is challenging by design.
Yes.
That friction isn't a bug in the text. It is the exact trigger for the myelination process we just talked about.
It is the feature, not the bug.
Right.
Yeah.
I want to really dig into the mechanism of the 2025 MIT preprint by Cosmina and her colleagues, because the physical results of this study are staggering. They actually hooked participants up to EEG machines to measure the electrical activity in their brains while completing cognitive tasks.
Yeah, they tested participants under 3 distinct conditions, using just their brains, using standard search engines, and using LLMs. The EEG scans revealed that the brain-only participants exhibited the strongest, most distributed neural networks. Their brains were highly engaged, lighting up across multiple lobes because they had to actively retrieve, hold, and synthesize information entirely in their working memory.
And what happened with the search engine group?
They actually showed moderate neural engagement. Because even with the search engine, you still have friction.
Right, you have to read the results.
Exactly. You have to parse the search results, evaluate the credibility of the sources, and mentally stitch all those fragments together into a coherent answer.
But the LLM users,
The LLM users displayed the absolute weakest brain connectivity.
that's crazy.
Their scans were remarkably quiet compared to the other groups.
We need to explain exactly why that happens. Like, is it just because the LLM hands you the final, perfectly synthesized answer, so your working memory never has to actually hold the variables and smash them together?
Precisely. The language model acts as an external synthesizer. It does all the heavy lifting of connecting the concepts for you, which means your brain never experiences the friction required to trigger myelination.
You are totally bypassing the physical mechanism of learning.
Yes. And the researchers tracked this over a 4-month period. They found that the LLM users consistently underperformed later on, and not just on the EEG scans, but at linguistic and behavioral levels.
Wow.
The researchers actually termed this the accumulation of cognitive debt.
Cognitive debt. I mean, I want everyone listening to deeply consider the irony here.
It's pretty stark.
We have an entire generation of AI researchers and ML engineers who spend their days trying to optimize and strengthen the dense connections of artificial neural networks.
Right.
But by relying on those exact same models to do their mathematical reading for them, they are literally demonstrably weakening the connectivity of their own biological neural networks.
You're trading your own neural density for immediate convenience.
It's wild.
And Schwer reinforces this with another 2025 study, this one by Vieru and Petrea, which looked at the broader impact of AI in academic environments.
What do they find?
Well, they acknowledge that AI offers high engagement and, personalized tutoring, but the costs align perfectly with the MIT EEG data. They found a measurable, severe diminishment in critical thinking skills and widespread over-reliance.
Because when the machine does the synthesizing, the human loses the ability to synthesize.
Exactly. So Schwer's conclusion is completely unambiguous here. When it comes to the specific task of reading and internalizing advanced mathematics, AI is not a shortcut. It is actively harmful.
The struggle is biologically non-negotiable.
If your goal is to truly understand a mathematical architecture, taking the AI shortcut essentially guarantees you won't actually reach the destination.
Man, let's pull this entire framework together for everyone. Reading math requires abandoning speed for the hours per page mentality.
Right.
We map the text on a sling in step 1. We interrogate definitions in a quiet room by hunting down adversarial non-examples in step 2. We deconstruct the causal blueprint of proofs line by line in step 3.
We act as our own ruthless compiler by writing the math out from scratch in step 4.
Exactly. And we manually rebuild the big picture in step 5, resisting the urge to let a language model synthesize it for us. Because bypassing that struggle just accumulates cognitive debt, literally weakening the pathways in your brain.
It's a framework that really forces you to respect the physical limits of how humans actually acquire complex knowledge.
Which leaves us with a genuinely terrifying question for the future of our field to mull over as you head back to your IDEs.
Oh boy, let's hear it.
We just established that the deep, frustrating friction of struggling through complex math is the literal biological requirement for building the brain density to understand it.
Right, you need the friction.
But we are currently building AI models that are getting remarkably good at outputting incredibly complex, novel mathematical architectures.
They're getting better every day.
So what happens 10 or 15 years from now if AI starts outputting advanced architectural proofs that are perfectly correct? But because an entire generation of engineers has outsourced the friction of learning for a decade, Humanity physically lacks the biological neural density to even verify them.
Wow.
Like, will human mathematical intuition become a lost art form, like navigating by the stars? Are we building a black box that our own brains will literally be too weak to open?
It's a chilling thought. I mean, we might be engineering our own obsolescence, not through, superintelligence taking over, but just through our own cognitive atrophy.
Definitely something to chew on the next time you're tempted to drop a dense 40-page PDF into a chat box. Thanks for joining us for this deep dive into the source material on AI Paper Slop. Catch you next time.